Good day everyone, I'm April Migalang Torres from BECE2C. I'm a reporter from Group 8 with a topic to be tackled about IVPs with Laplace transform or initial value problem using Laplace transform. It's now time to get back to differential equations. We've spent the last 3 sections learning how to take Laplace transforms and how to take the inverse Laplace transform. These are going to be invaluable skills for the next couple of sections. So don't forget what we learned there. Before proceeding into differential equations, we will need one more formula. We will need to know how to take Laplace transform the derivative. First, recall that f to the power of n denotes the nth derivative of the function f. We now have the following fact. Since we are going to be dealing with second-order differential equations, it will be convenient to have the Laplace transform of the first two derivatives. Notice that the two function evaluation that appear in these formulas, y times 0 and y prime or first derivative order of y times 0, are often what we've been using for initial condition in our IVPs. So this means that if we are to use these formulas to solve an IVP, we will need initial condition at t equals 0. While Laplace transform are particularly useful for non-homogeneous differential equation, which have Heaviside functions in the forcing function, we'll start off with a couple of fairly simple problems to illustrate how the process works. The particular problem we've been given the second degree function 2y double prime, or the second derivative of y plus 3y prime, or the first derivative of y minus 2y is equal to t of e to the negative 2t. We've also been given two initial conditions, y of 0 equals 0 and y prime of 0 equal to negative 2. Then I've gone ahead and written down 5 formulas that we're going to need, and I've gotten this from a table of Laplace transform. We're going to use the first 3 here on the left, f double prime t and f prime t, and this is t to the n and e to the at. We're going to use these first 3 to plug into our original function, transform it, and then we're going to use the second 2 over here on the right when we perform the inverse Laplace transform to solve for the function of f of t. So pretty self-explanatory here, at least in the beginning. We're going to take this formula here, f double prime t, and we're going to plugging in the right side of that formula in place of y double prime. Then we're going to take what's in the right side of this f prime t formula, and we're going to plug it in for y prime. And we're also going to make a substitution for y, but we don't need a formula for it. Then finally, we're going to plug in what's on the right side of this third formula here for what we have over here on the right side of our original function. So let's go ahead and make this substitution here. We'll start on the left hand side, so we're going to grab here first the 2. Now remember, we're plugging in this right side of this equation here for y double prime. So we'll say s squared, and since our original function is in terms of ys instead of fs, remember that f of s denotes the Laplace transform. But since our function is in terms of y instead of f, we're going to go ahead and use y in place of f. So we'll say y of s instead of f of s. So s squared times y of s minus s times y of 0, and then lowercase y because we switch to lowercase f minus y prime of 0. Now notice here, we have y of 0 and y prime of 0. We're going to be able to use our initial condition here in a second to plug in these values. 0 and negative 2 for those things, but we'll get to that in a second. So now we've got plus 3 from my original function times what we've got here in a second formula. So s times y of s minus y of 0, and then finally minus 2 times, on when we plug in here for y, we're just going to do capital Y of s. Alright, so we've made all our substitution from the left hand side. Now on the right hand side, we're going to use this formula that we've boxed in here, and we're going to change this format into the format here on the right hand side. So notice that in the numerator here on the right, we've got n factorial. So we're going to be looking at n here, but in our case that is equal to 1. We have t to the first power, so we're going to have 1 factorial in our numerator. And then in our denominator, we're going to have s. Remember, the s variable always stays minus a, and you can see here a is the constant. That is the coefficient on this t variable on the exponent. So in our case, a is negative 2. So since we have s minus a in our formula, we will have s minus negative 2, which is just going to give us s plus 2. And then that's all raised to the power n plus 1. We already know that n is equal to 1, so we'll have 1 plus 1, which is 2, and so that's going to be squared. 1 factorial, remember, is just 1, so let me go ahead and just change that to 1 right now. Okay, so now we've made all our substitution, and we don't need this 3 formula on the left anymore. What we're going to do at this point is use our initial condition y of 0 equals 0 and y prime of 0 equals negative 2. And we're going to plug in for these things here. We can make those and then we're going to solve for y of s, and that will give us our Laplace transform. So we will also kind of distribute this coefficient here, the 2, the 3, and the negative 2. So let's call this first 2s squared times y of s minus 2s times y of 0 we know to be 0. We have that there, so we plug in a 0 minus y prime of 0, which we know to be negative 2. So we have minus in negative 2, which is going to give us plus 2, but remember, we're multiplying by the 2 out in front, so it's actually going to be plus 4. Moving on to our second term, we'll say plus 3s y of s minus 3 times y of 0, which we know to be equal to 0. Then we have minus 2 times capital of y of s, and we'll go ahead and leave the right side as it is. 1 over the quantity s plus 2 squared. So now we'll simplify and solve for y of s. This term here, we're going to get rid of this. That's multiplied by 0. That's going to go away. This is 3 times 0, so that's going to go away. And if we now collect like terms, we'll have 2s squared y of s plus 3s y of s minus 2 times y of s, and then we have plus 4 equal to 1 over the quantity of plus 2 squared. Let's first actually move this 4 from the right hand side. We'll subtract 4 from both sides, so we'll get a negative over there. And just erase this and equals, now we go ahead and factor out a capital Y of s because we have it in each term, so we can easily do that. And now we're multiplying by 2s squared plus 3s minus 2. Let's go ahead and get a common denominator over here on the right hand side. So to do that, we will multiply the 4 by s plus 2 squared over plus 2 squared. And when we combine fractions, we'll just get 1 minus, just erase this, 4 times the quantity s plus 2 squared all over quantity s plus 2 squared. let's actually start multiplying up at the top. So we'll have 4 times the quantity s squared plus 4s plus 4 all over s plus 2 squared. And now we're going to divide both sides by this quantity here. 2s squared plus 3s minus 2 in order to solve for y of s. Dividing the fraction on the right side by this quantity here on the left is the same as multiplying 1 over that quantity. So we're going to have actually 1 minus 4 is squared minus 16s minus 16 all over the quantity s plus 2 squared. And bringing that quantity over right from left hand side, we're going to have this multiplied by 1 over 2s squared plus 3s minus 2. And now, since they are multiplied, we can just combine fractions. We get y of s equal to, and let's go ahead and consolidate here. So we've got negative 4s squared minus 16s, then 1 minus 16 gives us a negative 15 all over the quantity s plus 2 squared. We can factor this 2s squared plus 3s minus 2. If we do that, we'll get 2s times s, and we'll say plus 2 minus 1 gives us 2s squared plus 4s. So we'll say times 2s minus 1 times s plus 2. And if you can see here, we've got s plus 2 squared and an s plus 2. So let's actually go ahead and change this to s plus 2 cubed, and we can get rid of this s plus 2 to the first power here. So now, in order to go ahead and solve this initial value problem, we need to perform a partial fraction decomposition on this y of s function, or the function on which we already performed our Laplace transform. So we've gone on from our original function. We've done a Laplace transform, and here we stand. Now we need to use a partial fraction decomposition to solve this. So in order to do partial fraction decomposition, remember that we'll break apart our denominator here. And because we have a repeated linear factor here in the quantity s plus 2 cubed, remember that we will have to include all factors of lower degree. This 2s minus 1 is also a linear factor, but it's just a distinct linear factor. So that means that our partial fraction decomposition is going to look like this. Let's do the a over 2s minus 1 first. So we'll do 2s minus 1, then we'll have plus b, and remember we just need these variables a, b, c, d as opposed to ax plus b or something like that, because we're dealing with linear factors instead of quadratic factors. So b over s plus 2 plus c over the quantity s plus 2 squared plus d over the quantity s plus 2 cubed. And remember that all three of these factors here for b, c, and d are included because we have this repeated linear factor of the quantity s plus 2 cubed, and because it's cubed, we have to include s plus 2 squared and s plus 2 to the first power in our partial fraction decomposition. So because this is a Laplace transform problem, I won't take the time to do all of the steps of this partial decomposition, but let's just say that when we solve it for our coefficients a, b, c, and d, we'll get a equals negative 192 over 125. We'll find that b is equal to, let's just say that when we solve it for our coefficients a, b, c, and d, we'll get a equals negative 192 over 125. We'll find that b is equal to 96 all over 125. C is equal to negative 2 all over 25. But for the sake of putting all of this over 12, because it's going to make it easier on us, we'll get negative 10 all over 125. And then here for D, we'll get negative 1 all over 5, which we call negative 25 all over 125. And you'll see in a second why it's easier to have them all over 125. So now instead of this crazy fraction, here for y of s, we'll go ahead and plug in instead our partial fraction decomposition. And we're going to pull out 1 over 125 outside of our decomposition. Yeah. And now we'll just go ahead and plug in the numerator of all these fractions. Negative 192, positive 96, etc. So we'll get negative 192 over 2s minus 1 plus 96 over s plus 2. C is negative 10, so we'll get negative 10 over s plus 2 squared. And then D was a negative 25 minus 25 over the quantity s plus 2 cubed. Now, this is where our fourth and fifth formulas come into play. We have this formula here for 1 over s minus a equal to e to the at. We're going to be using that for the first two terms here, the first two fractions in our partial fraction decomposition. And then, we have the second formula here for n factorial over the quantity s minus a raised to the n plus 1. We're going to be using the formula for these two. And basically, we're going to be performing the inverse Laplace transform. That's the final step that we need to do in order to solve the function y of t and therefore have solved our initial value problem. So in order to do that, we need to make each of these fractions into the same format as the formulas we were given. So let's focus on these first two with the formulas here for 1 over s minus a. As you can see, 1 over 125 essentially, if we factor out this negative 192 and then the denominator here, if we factor out a2, then that would be multiplied by 1 over the 2 is factored out in the denominator. So we're actually going to get a s minus 1 half. Now this 1 over s minus 1 half is in the same form as in our formula 1 over s minus a, so we can easily convert it to a to the et. So that's what we're going to do with the 96 over s plus 2 as well. We'll factor out the 96 and what will be left with this is 1 over, and we could leave it as plus 2, but let's go ahead and say s minus a negative 2, which is the same thing. So we have it in exactly the same format as 1 over s minus a. So those are our first two terms, and we'll perform the inverse Laplace transform in a second. The second two terms here, we need to get into the same format as our second formula, and again, these formulas are from our table of Laplace transform. So in order to do that, keep in mind that we have this s minus a, so we'll do that. But then the exponent here, n plus, we need to figure out what n is in this n plus 1 exponent, and then make sure that our numerator matches that for this n factorial. So we're going to pull out a 10 and we're going to say minus 10 times. We'll leave the number for now. We can see we have s plus 2 here, so we're going to say s minus a negative 2 to get them into the same form. And then notice that our exponent here is squared, which is 1 plus 1. So if we have 1 plus 1, then we know that n is equal to 1. So we'll go ahead and say that we have 1 factorial in the numerator, which is just 1, and that's fine. So we have 1 over the quantity of s negative 2 squared. In our fourth term, we'll do the similar thing. We'll put out the negative 25, and then we got this multiplied by. In the denominator, we have again s minus a negative 2, then the exponent here, we have a3, which is essentially s2 plus 1. If we're looking at the exponent here, n plus 1, if our exponent is equal to 3, then n has to be equal to 2. So we'll leave this as a3, but in the numerator, say 2 factorial over 2 factorial, because we know from the n plus 1 exponent in the denominator that n is equal to 2. So we need to make the numerator n factorial, and the only way we can do that is by multiplying by 2 factorial over 2 factorial, and now we can pull out over those denominator. So now that we've converted everything into the same format as our formulas, we can go ahead and perform the last step of our problem, which is the inverse Laplace transform. So let's go ahead and do that. What we'll get is a y of t, which is going to be equal to 1 over 125. They will stay out in front. The negative 192 over 2 is going to be negative 96, and the around formula tells us that this part here that we've set up a 1 over s minus 1 half in the same format as this formula here, 1 over s minus a, and around formula tells us that this part here that we've set up 1 over s minus 1 half in the same format as this formula here, 1 over s minus a, tells us that a is equal to 1 half. So we're going to convert that 1 over s minus 1 to a to the 1 half times t. So we'll get e to the 1 half times t, and similarly we're going to have plus 96 times e to the negative 2t. Then in our second formula, we're going to have minus 10, and notice that we're converting it into something that looks like this. So minus 10 times t, so we have t to the first power, which is just t, and then multiplied by e to the at. We'll know that a is negative 2, so we have e to the negative 2t. And then for our last fraction, we'll have minus 25 over 2. And again here multiplied by t raised to the n power. Well, we know that n is equal to 2 because we have 2 factorial in the numerator, and because our exponent here in the denominator is equal to 3, and we know that n plus 1 has to equal 3, which means n has to equal 2. So we have t squared and then e to the at, where we know a to be negative 2. So we have a to the negative 2t, and that's it. That is our final answer. Again, we use our formulas here from the table of Laplace transform to perform the Laplace transform on our original function. We plug in our initial conditions, and then we had to use partial fractions decomposition to get our function to the point where we could perform an inverse Laplace transform. Once we perform our inverse Laplace transform, we get a function y of t, which gives us our final answer. That would be all for my sample problem about initial value problem using Laplace transform. We'll see you to the next problem.